Long-standing problem in contract theory is that wage schemes observed in practice are often simple, although the optimal contracts predicted by standard models tend to be complicated. The goal of this paper is to provide a novel perspective on this problem. We consider standard static moral hazard setting, but crucially, we assume that the principal observes fairly rich or precise data about agent's action. So in the perfect monitoring limit with infinite data, the principal achieves first best payoff. Away from this extreme limit, we are interested in which contracts allow principal to efficiently exploit rich but imperfect data, and whether simple contracts are enough for this purpose. The key novelty of our approach is that in order to capture efficient exploitation of rich data, we analyze convergence rate of the principal's payoff to the first best as amount of data grows rich. And we will ask which contracts achieve optimal convergence rate. Convergence rate is a useful measure of contract performance in data-rich settings because contracts with higher convergence rate yield higher payoffs for principal than contracts with lower convergence rate whenever the data size is rich. Moreover, achieving optimal convergence rate achieving optimal convergence rate itself is a less demanding criteria than optimal contract. So this creates a scope for some simple or more realistic contracts. So indeed, we show that optimal convergence rate is achieved by binary wage contracts, which are simple and widely used in practice. So this is somewhat related to the question Doron asked at the end of Hans' talk. And on the other hand, other common contracts such as linear contracts, which involve fine wage variation, yield highly suboptimal convergence rate. Let me turn to the setting. The agent chooses action from a finite set. The principal has access to monitoring technology mu, where each mu I is a distribution over signals and a chosen action A. We impose several regularity conditions, including the identification condition. The principal observes n signals xn, where each component is drawn IID from a distribution mu A. Here, this number n serves to parameterize richness or precision of data, which might represent the number of scans in automated control about workers' work effort, or the number of reviews submitted by students. But in the paper, we extend the results to more general monitoring structures. The principal is risk neutral and seeks to implement a target action, A star, by designing a wage scheme, W, which is a function from signal profile to wage level. Here, we have a lower bound on the wage scheme, which can be arbitrarily low. The agent has standard preference, which takes the form of additively separable form, which consists of consumption utility, which is increasing and concave, and effort cost. We also impose some regularity conditions, including the requirements that the target action is more costly than at least some other action A. Okay? And the agent has outside option utility 0. Okay. The principal chooses contract, which is a function from signal profiles to wage level, in order to minimize implementation cost of target action subject to IC and IR constraint. That is, the principal chooses wage scheme W to minimize the expected wage payment subject to Ishii, which says agent find it's optimal to choose A star, and IR, which says that agent expected payoff, expected utility is non-negative. The value to this problem is denoted by CNSB, second best cost. And it is well known that solution to this problem is in general complicated. Instead of solving for second best cost for given n, we are going to analyze the convergence rate to the first best as n becomes large. So let me introduce this notation for the second first best cost, CFB, which is the implementation cost under a perfect monitoring, which can be solved as usual in closed form. Clearly, when the number of signals is infinite, the principal is able to achieve the first best cost. The questions we are after are at what rate does the second best cost converges to the first best cost as n becomes large, and whether there are simple contracts that achieve the same optimal rate of convergence. Such contracts achieving optimal convergence rate outperform any contracts with suboptimal convergence rates as long as n is large enough. Okay. To state our main result, let me denote Cn binary, the second best cost, when the principal restricts attention to binary contracts, which are contracts with only two possible weight variations. And a couple of notations. So KL is the standard Kullback-Leibler divergence between signal distributions. And A minus is a set of actions that are less costly than the target action to the agent. The theorem shows that under both general and binary contracts, the second best cost converges to the first best exponentially at a rate given by this expression, which is the KL divergence relative to mu A star, which is minimized across actions in A minus. Specifically, the difference between second best cost and the first best cost and the general contract goes to zero exponentially with the rate given by this expression. And moreover, even restrict attention to binary contracts, the difference between the first best goes to zero exponentially with the same exponential rate. The first part shows that this minimum KL divergence is the optimal rate of convergence to the first best, which provides a simple summary statistics of monitoring technology, which captures the detectability of hardest to detect deviation to less costly action, because here we are minimizing KL divergence across actions that are less costly. The second line shows that the optimal convergence rate can be achieved. The same rate can be achieved on using binary contracts. Of course, the small O terms might be different, but they will be negligible as n becomes large. So this result provides a rationale for binary contracts, which are widely observed in practice. Just to be clear, for given any n, binary contracts are in general suboptimal. But the result says that any additional benefit from more complex contracts is second order under rich monitoring data. Specifically, when n is large, the benefit of optimizing over general versus binary contracts is smaller than the benefit of arbitrarily small fraction epsilon of additional signals, which is to say that for any epsilon, it follows that the implementation cost under the general contract is higher than the cost and the binary contracts combined with additional epsilon fraction of signals whenever n is large enough. Okay, so this result has some similar flavor with the classical result by Bureau-Krempler in the context of optimal auction. So in the paper, we show that in order to achieve the optimal convergence rate, binary contract must use lenient high versus low weight cutoff, which is in line with observed use of bonuses. Okay. So let me use a parametric example as an illustration. So here we have two actions, 0 and 1. One is the target action, and each signal is distributed according to normal distribution that is centered around the chosen action. And here I'm plotting the implementation cost as a function of n. This blue graph plots the implementation cost under the binary contract, under which IR and IC is binding. And it has a property that high wage is paid if and only if the average realized signal is about 0.1. So this binary contract is quite lenient. To see this, note that the expected value of this expected value of average signal and the target action is 1. But the expected value of average signal and the deviation action 0 is equal to 0, which is just below this cutoff. So in this orange curve, on the other hand, is based on binary contract in which the cutoff is half, which is exactly in between the expected average signals and the action 1 and action 0. And here we can see that under lenient binary contract, the implementation cost converges to fast pace much more faster than the symmetric binary contract. So let me provide a high-level intuition behind the role of leniency in the context of this example. If we use more lenient high-low wedge cutoff, this entails the following trade-off. First, this entails a higher probability of false positive, meaning that this is the probability that the average signal goes above the cutoff, even though agent deviated to action 0. So this higher probability of false positive makes deviation action more attractive, which is clearly harmful for IC constraint. On the other hand, leniency also entails lower probability of a false negative, which is the probability that the average signal is below the cutoff, even though the agent follows the target action. Okay? The lower probability of false negative makes target action more attractive to the agent, which is variable for both IC constraint and IR constraint. So in general, clearly, for given n, the choice of cutoff should trade off these two probabilities. But the key finding is that whenever n is large, reducing false negatives will be the dominant consideration for the principle. The basic idea is that as monitoring improves, IC constraint becomes less and less important to the principle as it approximates perfect monitoring, which makes the false positive consideration less and less important. Okay. So it will be optimal to choose maximally lenient threshold as n becomes large. Okay, let me turn to another important class of contracts, which is linear contracts. So here, let me denote Cn linear. That's the second best cost when the principle restricts attention to linear contracts. Here we define linear contracts as those in which the weight is additively separable across signals. For example, a special case of this is when the weight is equal to the fixed fraction of average signals, assuming that signals are one-dimensional. So the proposition shows that under linear contracts, the second best cost converges to the first best cost sub-exponentially, meaning that there exists some constant such that the gap between the first best cost is no less than k divided by n with additional small o term. So to be clear, both binary and linear contracts can achieve first best when n is infinity, but away from the limit, linear contracts are much less effective at exploiting rich data than binary contracts. So immediate implication is that whenever n is large, the implementation cost under linear contract is higher than the cost under the binary contract. So this is an illustration based on the previous example. This green curve is the implementation cost under optimal linear contract, which converges to the first best, but at a slower speed, in particular compared with lenient binary contract. Sorry, how long? 2 minutes. 2 minutes. Okay. Just let me say that the theorem 1 immediately implies the following ranking of monitoring technologies that quantify the value, the monitoring value to principal under data-rich setting. Specifically, take any two monitoring technology, mu and mu prime, which has the properties that for any pair of actions, the Kerr divergence between signal distributions are higher under mu than the mu prime. Then for any U and C and target action, whenever M is large, the implementation cost under mu is lower than the cost under mu prime. So the point of this comparison is that this holds robustly across agents' risk preferences, effort cost, as well as target action. And the characterization is based on statistical simple measures using Kerr divergence. Perhaps let me skip the discussion of the literature for the sake of time and let me conclude. So this paper provides a new perspective on the use of simple but suboptimal contracts, showing that under rich monitoring data, there is a negligible performance gap between optimal and binary contracts, in contrast to linear contracts, which are highly suboptimal. And also one derives a detail-free ranking of monitoring technologies. This type of approach based on convergence rate analysis to the first best may provide rationale for simple contracts and mechanisms in other domains. For example, we have another recent paper that studies multidimensional screening with rich consumer data, where we show that the pure bundling mechanism achieve optimal rate to the first best, while other simple mechanisms such as separate cells achieve only suboptimal. Thank you so much.
Thanks a lot. Do you have a question? So in your model, the agent takes the action in the beginning and once and for all, and then all these. And, have you thought about like how things work out if you allow the agent to like take, change
Yes,
new action?
That's right. That's a very good point. So we have result in the paper which is partially addresses your point, but the agent can adjust their actions, but much less frequent relative to the number of signals, where the result will be basically the same. We are currently working on the case where, at every step, the agent changes action, and there the analysis is a little bit different, and actually linear contracts perform quite well in the setting. So it's a little bit different. Yeah.
Cool. Thanks.